All right. So we're going to do the second part of this chapter. It's on binomial distribution. So we got a big chunk of new stuff today. And then tomorrow I won't be here. And so you'll have that video for that. Now, the assignment that goes with this is pages 51 and 52. There is one little small correction I want to make on a typo on the first page, and I'll tell you that at the end of the video. Well, actually, you know what? Let's go ahead and fix that now. Turn to page 51 real quick for me, please. And if you look at page 51, then the typo I need to fix is the very bottom of the page. The last problem, F, on page 51, has I think C and D written there, but it needs to be part B and part C instead. Okay, so because we're going to compare doing probability two different ways and see how close they are to each other. All right, so let's go ahead, and this first thing I want to discuss with you, you don't have in your notes page, but I want to first mention to you about this stuff called discrete versus continuous. Discrete probability, this is what we've been doing recently. It is finding the probability of whole number events, like the probability of having 3 people that meet this criteria, the probability of getting exactly 6 eggs amongst the dozen that are whatever. And so what happens is when you have whole number of items, then a graph of that data would look like this, where you have like a histogram because you have one item, and so the probability of 1. You have 2 items, so the probability of 2. You have 3 items, so the probability of 3, and so on. But what do you see I have on top of it superimposed is what looks like a what? The normal model. Normal model probabilities are continuous, not discrete. That's because they're all possible numbers, like they can even be decimal values. Miles per hour, the average miles per hour, the distance, the miles per hour could be like 23.4, 23.44, 23.45. It can be all of these little in-between amounts. So you have all of these in-between sections, not just those whole number bar lines for a histogram. Okay. So that plays into what's going on today, because what we've been doing this chapter is the discrete probabilities. And in today, we're going to eventually try to approximate a discrete probability with the normal model and see how close those are, because normal model math is easy in a lot of cases. So let's go to what you do have on page 48. So here we go. We want to review the criteria for these discrete probabilities. Review the criteria for those discrete probabilities. Bits and bins, what's the B standing for? And so what is that telling me? 2 successes or failures. We have 2 choices, success or failure, okay? Next is independent. How do you write that out correctly? Not just one affects the other, or one does not affect the other. Good. One event has no effect on the probability of the other. One event has no effect on the probability of the other. All right, and the bits or bins, that third one tells us the difference between if we're dealing with a geometric or binomial, which is what we're learning today. Do you remember what made it geometric? You do trials until there is a success. That's geometric. Trials until a success is geometric. But today, we will be told a set number of trials, we'll say out of 10 people or out of 15 people or whatever, what's the probability that you get exactly 3? So out of a set number, what's the probability you get this many? That's binomial. And then recall that our same probability is dealing with making sure that if you have a small sample, you're replacing those items. For example, if I just had 10 M&Ms in my hand, would the probability change when I take one of them out and eat it? Okay, but if I had a whole assembly line of M&Ms, and I know that the company makes 24% blue M&Ms, and I have the whole assembly line, or think about that, like that whole thing going out of the factory. If I take one out of that whole billions on the assembly line, is that going to change the probability that the next one I picked is blue? Probably not, because it's like such a huge sample. Taking one little M&M that's rolling off the assembly line ain't nothing. Okay, so we had to be careful when we have small samples. All right, let's go on to today's and talk about what is this thing that's so special about the binomial. All right, so we know we have this situation. We're going to talk about this situation where we have the express checkout lane at the grocery store. You know, it's 5 to 7 p.m., coming home from work, forgot to cheese for the tacos or whatever. You got to pick up just a couple things. So you're going to go through the express checkout lane. In fact, about 25% of people go through the express checkout lane. It is Tuesday, so Taco Tuesday, there you go. So 25% are going to be going through the express checkout lane. All right. So amongst 5 customers, we're going to talk about the customers who use the express checkout lane. And I know you know how to do this first one. So do this. Find the probability the express checkout lane is not used until the 4th customer. What type of probability is that? Geometric, because it's going until. So compute that real quick. Okay, so 0.75 to the 3rd and 0.25 is the 4th. So that's 0.1055. All right. Now, let's read this next situation. In a really small area right here to this, in this little section here, I want you to write what you think the probability of getting exactly 2 successes is out of that 5. So just take up this small little space right here. Write the probability of exactly 2 of the 5 customers using the express checkout lane. So what did you put for that? What did you put there? I have 2 successes, so that's what? 0.25 squared. And then what? 0.75. So there's my successes and then my failures. Okay, so here is the successes, and I had 2 of them. And then here's the failures, and I had 3 of them. Okay, the problem with this is that right there is mandating that those 2 are in one particular place. That would be like saying the first 2 customers are going through the express checkout lane. There are many different ways amongst the 5 that you can have 2. So where are, amongst these 5, where are these 2 successes located? Let's explore that. I want you to first draw yourself, let's do 4 sets of 5 customers, spaces. Do spaces for 4 sets of 5 customers, and let's see what that does for us. All right, so amongst these five customers, where could my 2 express checkout lane customers be? They could be the first and second. What else? Well, I kind of go like first and third, first and second, first and third, and then what? First and fourth, and then first and fifth. Is there more combinations? Then figure it out. Go, draw some more. Figure out how many more combinations there are. So I found, how many different ways did you find? I found 10 combinations, 10 different ways that there could be exactly 2 customers that go through the express checkout lane. So that means I would have to take this probability and have that happen 10 times. Because it could happen the first way or the second way or the third way or the fourth way. So to find the probability that you have exactly 2 is 10 times that 2 successes times the 3 failures. That is how you would do a binomial situation. So of that, what's most problematic if you were to say do this a problem again with say 15 customers? What do you anticipate being the hardest part? Yeah, running out of spaces trying to make all of the what? Combinations. Holy moly. Oh my gosh. It gets very large very quickly. In fact, 10 choose 4 is like 210. Okay, crazy. So we have a formula to help us figure out how to do that so we don't have to draw them all out. So let's take a look at this here. Okay, so I actually am going to erase this so I can scoot this up and have more room. Okay, so here we've got a situation where we have a formula to help us figure out how many combinations there will be. And so a common notation is this right here. This is in combinations of 5 successes, or no, sorry, 2 successes is what we did. 5 combinations with 2 successes. Okay, so what is that N representing? So N is actually our number of trials, which in this case is our number of customers, picking a customer. And what did K represent? It's the number of successes. In our case, a success was somebody who does what? Uses the express checkout. Okay, so let's figure out how to do this. So you could write this like 5 choose 2. So a couple of things I'm going to write. You would say this, N choose K successes. If you were to say that, N choose K successes. And I also want you to notice there is no fraction line. If you put a fraction line, it's wrong because what's 5 divided by 2? What's 5 divided by 2? Yeah, excuse me, 5 divided by 2 is 2.5. Is that how many combinations we have? No. So no fraction line. No fraction line. Okay, well, what in the heck is this other stuff? N, in our case, is 5 with an exclamation point. What does that mean? Does that mean me going You know, I do get excited a lot in here. But is this saying that I have the right to go 5? 5. Is that what's going on here? Am I excited about 5? Okay, why not? That's true. That is called a factorial, and you may have seen that before in math. If not, then here's what that means. Anybody know what that means? Oh, what is it? It is. It's so fun. It's 5 times 4 times 3 times 2 times 1. I think that's a way to get excited because it's so fun. 5 times 4 times 3 times 2 times 1. Okay, now on the bottom, we have the success number, which in our case was 2 factorial. And then here's the failure factorial, which is 3 factorial. So let's see what that would be like. What's 2 factorial? 2 times 1. What's 3 factorial? 3 times 2 times 1. So what do you notice? Well, it is going to take forever for a little bit of time until I teach you a shortcut. Okay? But you can't appreciate the shortcut until we have the pain of this real way. So do you know that because these are all multiplying, what do I have the right to be able to do with them? I can cancel them. If there was addition signs in here, could I cancel them out? No. As Miss Miser would say, if you have addition signs in here, that'd be killing puppies because you cannot just cancel out those things. It would be like that. So, but they're all multiplying, so I can. All right, so that's 20 divided by 2, which is, oh my gosh, guess what? 10 combinations. Now, it is a coincidence that 5 times 2 is 10. That's not why it is. That's a coincidence, so don't think that's the magic answer. Okay, so look, I could figure out the number of combinations without drawing them all out like we did earlier. Yay. So let's go to the top of the next page and just finish that out. So we're going to write up here. Real quick, we'll just say complete that probability. What did we have? We kind of did this in depth. We had 10 combinations. Okay, and then what came next? Multiplied it by the successes, which was our, how many were in the express line? 25, and there are 2 of those. 0.25 is the probability, and there's 2 of them. And then what? 0.75 is the failure, and there were 3 of those. And so when you multiply that all out, you get 0.2637. So if you go to Brookshire's or whatever, there's a 26-ish% chance that exactly 3 of them, or 2 of them, will be going through the express checkout lane. Okay, hey, before we go on, let's just review. This first thing here is this first number is your combinations. This second number here represents the what? Successes, success probability, and how many there are. And this third number here is representing our failures. So you can always keep it sorted that way. And that's always that way. It's consistent. So I want you to take a look at this next one. So now we have a new situation. Suppose 75% of all drivers always wear their seatbelts. Let's investigate. How many of the drivers might be seatbelted amongst 6 cars waiting at the traffic light? Find the probability that exactly 3 of those 6 cars are wearing their seatbelt. So the probability of wearing a seatbelt is 75%. Okay, so what is N? What is our number of trials in this problem? It is 6. Good. And what's the number of successes we're interested in? 3. So our K is 3. So you need to find the combinations and so on and so forth. So do that out like you think. So you may fret and say it's going to take forever, but I am super happy to just do that and determine there was 20 combinations than having to draw them all out. Yeah? Okay. So there's our that. Let's now, so 20 combinations. 3 of them wear their seatbelt, so that's 0.75 to the third power. And 0.25 is the failures. How many, if there's 3 successes, how many failures are there? There's 3 because it totals to 6. So FYI, the success and failure exponents will always total to the number of trials. Okay, so that 3 plus 3 is always going to total up to your n. All right, when you multiply that out, you get 0.0162. So 1.62% chance that exactly 3 of them will be seat belted. All right, questions on coming up with that? Now it gets even better because now I'm going to show you a formula that you can write and then punch a few buttons in your calculator and plop out the answer. Okay, so here we go. So hopefully, we appreciate the n choose 5 or 5 choose n choose k formula, the factorial formula, because we don't have to draw out the combinations. But now I'm going to have you do this other thing and you'll appreciate it. Yes. Oh, poo. I have a wrong answer? Well, dadgummit. Oh, I know why. Sorry, my bad. Okay, hold on. It's not that answer, is it? It's 0.1318. Is that better? Ah, I was jumping ahead. I was too excited because I did sorry, my bad. I did the next one. Will you do the next one real quick? Find the probability of exactly 4. Yes. I was so excited. Too many exclamation points going on around here, okay? So do this one. Find the probability of exactly 4 of the next 10 cars wearing their seatbelt. I was wondering why I was getting so many perplexed and concerned faces. Good job, Abe. You saved the day. Because I would hate to have that mistake on the recording. Yeah, and not have it fixed. So it's on there, but it does get fixed. $210 combinations. Aren't you glad you don't have to write all those out? Guess what that answer is? That one is the 0.0162. That I was ahead of myself. Okay. Questions there? All right, now let's go to this little formula here. This is on the formula chart. So I'm going to show you the work you have to show, and then you can click some buttons in your calculator to get the answer. But you do have to know how to write the formula and so on. So look at what happens here. So N is what we have been saying. It is the number of trials. Okay, so N is the number of trials. But instead of saying K successes, the College Board changed it over this year and say X number of successes. But it is all over the internet with K successes and such, and other texts use K as a common letter to represent successes. So I wanted to leave it in there. so as to expose you to that possibility. So X is the number of successes and P is the probability of success. So let's look at this formula here for binomial distributions. This is exactly how it shows on the formula chart. Okay, so we can see here, you will write the probability of what you're finding. And then this parentheses thing here is your N choose X successes. That, what I have highlighted in yellow, represents how you compute the combinations. Okay, so that what I have written in yellow is the notation for combinations. Recall, no fraction line. Okay, now what I have highlighted in red here is the success probability to how many successes you have. And then what I have highlighted in blue is the failure probability. So that's what we've been doing. I just wanted to show you how it's notated on the formula chart. So all we will have to do when we do a problem is write out that formula, and then I'm going to teach you the click, click, click easy buttons in the calculator to get the whole answer. You won't even have to compute combinations anymore. Okay? All right. You didn't think it got any better, but there it is. So let's do this. Here we go. Let's say we have the same thing up above where we're wearing our seatbelt at least 75% of the time, but in this case, 75% of drivers wear their seatbelt. So here we go. Oops, I want to erase this here. Okay, so the question says, what is the probability that there are exactly 6 drivers amongst the first 10 wearing their seatbelt? All right, so N is 10 because that's a total of 10 trials, 10 drivers, and they want exactly 6. So here is how that formula goes. I start off saying what I'm finding. I'm going to find the probability that I have exactly 6 successes. Okay, so that's what I'm finding. Now, what's the next part in the formula? The combinations, and that's N choose X successes. So you just write 10 choose 6 successes, no fraction line, no fraction line. Okay, what's next in the formula? The probability of success to the number of successes. So what is the probability of wearing your seatbelt? 0.75. And how many of those do I want? 6 of them. Okay. Now comes the failures. So that's the failure probability of 0.25. And if there are 6 successes, how many failures? 4, because recall, failure number plus success number is the total number, always. Those exponents always total to the n. Okay, now here comes the magic. I'm going to write down the calculator steps, and then we'll go compute it. So we will go to Binomial PDF today, and the way it gets written is it'll first have the number in the number of trials, the probability of success, and how many of those we want. Okay, so let's go do that. So to the calculator. Where were all of our other distribution functions? Second vars. Okay, it's pretty much in the middle of the list. So you can go down or you can go up to binomial PDF. There's binomial CDF, which we'll learn about tomorrow, binomial PDF today. All right, if you have a menu, the first thing in your menu says what? Number of trials. And so how many trials? We have 10. If you don't have a menu, you'll see what I'm doing up here. If you have a menu, what's the next thing? P, that's the probability of success. So we up here put a comma, and our probability of success was 0.75. If you have a menu, what's the third line? X value. That's your number of successes. So if you have a menu, okay, then we were wanting that. But for those of us who don't have the updated operating system, or we have stats wizards off, there it is. And ta-da! There is our probability. There's about a 14.6% chance that you're going to have exactly 6 of those 10 wearing their seatbelt. And we did not have to do all of that other computing. Wasn't that good? So nice. But you have to write that formula. And then you have the luxury of doing that in your calculator. So I want you to do the next one. Write the formula out and compute and see what happens. There are 4 people not wearing their seatbelt. If you have 6 people wearing their seatbelt, how many are not wearing their seatbelt? 4. So does it surprise you that answer to B is essentially asking the same question as A? Yeah, so they came out. Now, you might write them differently when you write the formula, and you would. You would go 10, choose 4 successes, 0.25 is what you were looking for, and there are 4 of those, 0.75, and there are 6 of those, and so on. So isn't that interesting? So quote unquote, the success, or like what you're looking for, is the not wearing the seatbelt ones. And it comes out to the same answer. All right. So let's have you try this. How are you going to do exactly 4 or exactly 5? In fact, I think I'm going to shortcut us right now, and we're not going to actually compute this. Let's see who's going to tell who. Odds, tell the evens how you would do part C, and then we'll discuss. You don't have to actually do it, though. Okay, go. That's right. Okay. So odds tell the evens. So the evens tell me, who's even here? Okay, go. What you got? There you go. Solve for 4, solve for 5. You're going to have to write out the formula twice, and you'll add them together. Okay? So for right now, you don't have to do this because we're about to do this in a minute. Very good. So let's now go on to the last idea of the day. And it is about, we're going to get to where we use the normal approximation for the binomial. So let's actually start on the next page up at the top, where we have the formulas, and this is what's given to us on the formula chart. What do you notice? So this is exactly the way it's on the formula chart, these 3 boxes in a row. So what do you notice I just highlighted here? That box that I just highlighted is what? That's the formula we just did. Very good. So that's the formula we just did with your combinations, successes, and failures. Okay, good. Now, beside that is the mean. Well, remember that yesterday I talked about expected value is the mean. So if they say, how many do you expect out of 10? Then that's what you would do. And that number can be a decimal because that's how many you expect on average. And then beside it is the standard deviation. All right, so let's go through this last process. The first question is referencing the babies in hospital. So we have 10 babies that are born at Harris Methodist Hospital. And so I want you to go ahead and go through the process of the probability. And so FYI, boys and girls are equally likely. So the probability in this case of a boy, we are told, is 50%. Okay, so go through the process to find the probability that you will have exactly 7, 8, or 9 babies that are boys out of those 10. Okay, so do that. I'm going to give you a few minutes for that. About a minute and a half. So this is your success probability, and that's the number of successes you want. And that's the failure probability, and then the number of failures. No, 0.5. It's the probability 0.5. To the seventh, right. There you go. Yep. Yeah, no fraction bar there. Okay, that's okay. And so 0.5, and how many of those do you want? 7. Mm-hmm. So when we're talking about babies, would that be considered discrete or continuous? Discrete or continuous? Discrete are exact numbers of things, while continuous can be little decimals. So when we're talking about the number of babies born, what's that going to be? Discrete, see? So discrete probability, it is appropriate to estimate this with the binomial, with this method, okay? Because we have the probability of the 7 plus the probability of the 8 plus the probability of the 9. And so that's about a 17% chance that 7, 8, or 9 of the babies, the 10 babies, will be boys. Okay. But now what we're going to do is say, what would happen if we tried to approximate this with the normal model? So in order to do normal model, I need a mean and a standard deviation. So according to these formulas up here, the mean and standard deviation, what would that be for these 10 babies? The probability of it being, how many boys on average would you expect to be born out of 10 babies? Does it make sense that if it's 50% boys, you would expect on average there to be, on any given day, you expect there to be about 5 boys out of those 10? Okay, and then I can do the formula for standard deviation, which is that. So there's my formula for standard deviation. I get 1.58 boys on with that standard deviation. So I want us to take a look at this picture I have drawn here. So what I have in purple here represents the discrete probability of the 7 boys plus the 8 boys plus the 9 boys added together. And so that purple is the discrete, the binomial, okay? And so that was 17%. But look what I have done with my normal model. I have put it on top of it in an attempt to say, hey, I wonder if we could estimate this with the normal model. So let's see. What would you do if I asked you to make a normal approximation with 7 to 9 boys. 7 to 9 boys. How would we do that if we just had that problem on our Chapter 6 test? We have a mean and a standard deviation. We have a mean, standard deviation, 7 to 9. What's the probability from 7 to 9 boys? Get your z-scores. Okay, so how do we do that? Z-score for 7? Yep. 7 minus the mean over the standard deviation. X minus the mean over the standard deviation. So that's 1.27. Okay, and so that is about right here. So there's my z-score for 7. Okay, at 1.27. Okay, then what else? Z-score for 9. 9 minus the mean over the standard deviation. 9 minus the mean over the standard deviation. So there is that. And how do I get, so it's 2.53. How do I get this area, this probability, this proportion of observations from 7 to 9? How do I get that area there? I norm CDF from the low z-score to the upper z-score, and it's 9.7. So this red area is 9.7. What do you have to say about the comparison of the purple to the red? Yeah, I'm not liking it too much. That interesting. So in this case, the normal approximation to the binomial wasn't like really that great. I mean, it got me in the ballpark, I guess. But, you know, it's 6%, almost it's 7 percentage points off, over 7 percentage points off, almost half as much as it should be. But you know what? So that's okay. We're going to do a couple of these over the course of the homework. You'll do 2 more of these over the homework, and we're going to discover when does this normal approximation fit the binomial better. What happens that my normal approximation starts getting closer to the binomial? So then it's an okay way to do that. So we'll discuss that when I get back. But your assignment, if we look at pages 51 and 52, what you're going to notice is that you do a couple of binomial probabilities. So here's a binomial and a binomial, and then guess what you do? You estimate it with the normal. And that happens on the back. You do a binomial, and then you estimate it with the normal. And so we ultimately are going to compare how well did this normal model estimate that binomial. Okay, so there's your assignment, pages 51 and 52. Please make sure that you did the correction on this bottom of the page, 51, so that we can compare the binomial to the normal.